about the Graal Cloud, and the idea is that we want to extend the notion of the Java platform to the cloud, and I call it a Java-based platform using Graal technology. And so some of the problems I think that we have with building cloud apps, are coming from the fact that it's a much more complex environment. And so common functionality like logging, file system, file storage configuration, we've moved from local libraries that just read stuff from files to making all those things network API calls like over REST. And you have a new stack of open source software dependencies which have kind of varying levels of support. And so there's more engineering effort to maintain and optimize for those libraries. Cloud is really interesting, I think, for a lot of people because it has this cool business model that I think is best captured by serverless, where you just pay for what you use. But that creates even more complexity for developers. You have to make your apps stateless, you have to kind of do much more explicit state management. You have to deal with the fact that your applications are going to time out, and you have to worry about cold starts. And then a lot of the cloud has been built on this container platform, and mostly of which you're supposed to keep them immutable. And the problem that we see with containers is they kind of obfuscate the customer application from the cloud provider. So for example, if the cloud infrastructure wanted to automatically set the size of the Java heap, well, that was actually set by some bash script that was called, when you provisioned your container, and that called Java with some flag, and we don't know how to parse that out. We don't know how to kind of pierce the container abstraction as the cloud provider and change that and say, hey, I see here you don't need a gigabyte. You could get away with only 200 megabytes. It's hard for the cloud to automatically do those kind of changes. And kind of I like the Cloud Native Computing Foundation landscape map because it just shows you how many different pieces you have to kind of put together to build cloud apps. So there's three pieces that we talk about with the Graal Cloud Stack, and the first one is the stuff that we've had for the longest time, which is GraalVM Native Image, which is our ahead-of-time compilation and snapshot tool. It's not just an ahead-of-time compiler, we're also snapshotting state of Java programs. And so I think the most important things about native images is making startup and memory footprint for Java programs about 3 to 5 times better. And I think in the cloud, one of the things that's often not as talked about, but it's very important, is that you get faster programs when you care about the P99th latency or the P99 9th latency. And so throughput now, I think in the last year or two, we got to the point where just peak throughput at P50, i.e. the average throughput, is now surpassing conventional Java running in hotspot. But because you have less variance because you don't have a JIT compiler, at P99 and P99.9 you get a lot of advantages. Another big advantage of running native image in the cloud is that because the code pages are read-only, you can share them in a lot of different runtimes. Now the big negative we've had for native image in the past that I think people still are complaining about that we still have today is build time. It takes longer to kind of go through a compile debug cycle with native image than it does with conventional JIT compilation, which was the problem that JITs were originally built to solve. But we have a new technology coming out called native image layers that I think addresses that problem pretty well. And we're starting to get really good ecosystem support now for native image. Actually, this is a little bit older slide, but commercial support for Spring and all the cloud vendors' SDKs have been done in the last couple years. And so I think the support from the ecosystem for native image is doing really well. And so it's really great that you have all these benefits from native image, but some of those advantages are kind of hidden if you stick them in a container. And Lambda still is taking, even if you're using snap start, it still takes on the order of 100 milliseconds to start apps, and that's kind of already kind of more overhead than native image is. So continuing to improve native image, startup time wouldn't help if you're putting it in a runtime that's going to cover that up with its own latencies. So we've been working on a project now called GraalOS for a couple years, and we're getting close to launching this thing hopefully later this year. And basically, it's an alternative cloud runtime to containers and Kubernetes. For apps that are built on Graal technology. And so the idea is that, especially for cloud services that have variable usage where your usage pattern is spiky, it's not completely flat, you'll see some substantial runtime cost improvements. We have a very aggressive cold start time we're targeting. I'm hoping we can still get there. Still looks okay. Fundamentally, we want to keep the Java state on network storage so we can do fast suspend and restore and migrate. And we want to get the infrastructure cost a lot lower than serverless platforms. Like today, using serverless, it's like 4.5 times the cost per CPU hour is just renting a VM. So the serverless platform itself adds a lot of cost over just renting the cores from a cloud provider. And so we think there's a lot of margin there that we can attack with a better kind of serverless runtime. And that means we don't have to keep hardware provisioned because a request might show up, and that can keep the cost lower. And then the third thing is kind of our fork of Micronaut. We're now renaming it to Graal Developer Kit for Micronaut. We announced that a couple weeks ago. We used to call it Graal Cloud Native. But basically, we have our own build of Micronaut and all the dependencies, which you kind of need to build cloud apps. It includes Netty and the Jackson JSON parser and the cloud vendor SDKs. And so, I think one of the reasons it's interesting is that frameworks, Micronaut, like all other ones, make HTTP APIs look like Java function calls. You annotate your Java method with like a URL and say @get or whatever, and now it's a get endpoint for HTTP. It's also a nice integration point for all these third-party libraries. And we chose Micronaut because it's designed around avoiding all runtime initialization, and that's something that really helps us get faster cold starts. We're trying to focus on the Java developer experience as opposed to a generic cloud developer experience. Now, one of the things that we have to do is that because we care about really fast cold starts, there are a lot of older Java libraries that are expecting to run in some long-running Java platform like WebLogic. And so they do a lot of work at runtime. You fire them up, their class initializers are going to start parsing XML files or creating connection pools or a bunch of other stuff that makes runtime latency higher. And so you need to curate the set of open source, kind of all the dependencies underneath the frameworks so that we can get that cold start cost down towards 0. And I think a lot of libraries have been trying to avoid runtime initialization, partially because of native image, and that's been good. But there's still gaps, and so we need to kind of address those. So we're using Micronaut now pretty widely within Oracle. So NetSuite and the RDBMS are some of the bigger users, but they're being used in some of our apps, like the former Cerner healthcare unit that we acquired a few years ago is using it aggressively. Oracle Cloud's using it aggressively. And we have a supported distribution, and you can go get the Oracle builds at Oracle Maven. So the idea is that you have this new cloud platform with these 3 layers: the runtime, the developer kit, and then native image. And then it kind of fits in like the rest of the cloud in that all those services that you see at the bottom are provided by the cloud vendor, Oracle Cloud, Amazon Cloud, whatever. You're using load balancer, and those are kind of replacing the Java developer kit, right? So rather than using JDK types of APIs as your platform, the cloud becomes the platform, right? And there's a lot of basics of cloud programming, like what do you do when your service call times out? How do you handle getting authentication credentials from a vault? And you get identity tokens, and there's a lot of overhead and procedure that's required to build cloud apps that we want to just integrate in the platform for you. You have to give off heartbeats to the load balancer, and you have to communicate with the API gateway, and you have to plug into logging in metrics and security monitoring. There's all kinds of junk you have to do just to be hello world as a cloud service. The hello world cloud service is actually quite complicated, right? And because it's a runtime, the idea for the Graal platform is that we can always profile and audit your app and run experiments. So, one of the things that's interesting about Java is you can actually trade off DRAM usage for latency. So if you say, hey, I'm willing to take a little bit longer time to service each request as long as I can use less DRAM. And DRAM actually is more expensive than CPUs right now, and it keeps getting worse. So can the cloud help you make that trade-off for you? Right? And so we want to be able to do that and build models of that and conduct experiments and dynamically re-optimize. We have a profile-guided optimization feature in native image that's been out for a little while. We want to have that just done automatically for you so you don't have to deal with it. And then we can automatically regenerate a more optimized native image with PGO optimization and redeploy it for you all the way. And so the big difference here, though, is that Java is the cloud abstraction and not Linux containers. So to develop with GraalOS, you can just write your hello world program in your IDE, upload it to Oracle Cloud or any other cloud vendor, Right now we're just targeting Oracle Cloud since that's where we're working out all our bugs. And that native image on the server side in the cloud will compile and optimize your app and will run it when invoked. It'll work with all the standard tools. We do have some integration with OCI's CI/CD platform so that if we want to rebuild native code, we can just go build it for you, retarget it for various shapes. We want to always be able to rebuild your code, which is not a big deal for Java programs, but if you have native libraries underneath them, which Panama and other Java features enable, we still want to be able to recompile that stuff for you as well. So you give us your bytecode, or you give us source, if you want to give us native code, and you give us a deployment descriptor, and the deployment descriptor says, well, how do you provision it? How do you want it? And the most difficult thing often is network configuration. If you actually tried to build a cloud program, and you see, oh, I have this virtual compute network, and I got to set up these networking routes, it gets really complicated. So we have a simplification for networking, at least in Oracle Cloud, to where we have public, protected, and private networking modes. So we kind of reuse those Java abstractions for how to provision the networking in the cloud. You can get an internet-facing IP address with public. There's a typical unit of deployment that's common in Oracle Cloud called a compartment. And so you can just say, well, anything in this compartment is accessible with a network, and so that's another simplified version of networking. And if you really want to go to a private network and have a custom network routing rule and custom firewall rules on all your endpoints, which big enterprises can do, you can do that as well. And then you tell us how fast you want each endpoint to run, how long it can wait to service a request, and that's really the target that we'll optimize for you. Now, when you give us your code, we'll run native image to build it for you. And there are a bunch of different machines that we have available in our cloud, and so we'll rebuild it for different processor architectures. One of the things that's kind of unfortunate about the way we build native code today is we often compile the target for an old version of a processor. So, okay, I'm going to compile it for a 10 or 15-year-old version of an Intel processor, and only people that really, really care about it, like maybe linear algebra toolkits, will actually compile code for the latest processor generations because they don't want to deal with different versions of the ISA. So we can do that for you. That's one of the things that JIT compilers give you. We want to give you that as well. And we have our own version of libc that works in GraalOS. One of the important features of the way GraalOS works is it's what I call compiler integrated isolation. So the compiler is needed to help enforce some security guarantees. And I'll talk a little bit more about how that works. But it allows us to do much faster context switching between trust domains if we know that all the different pieces of code that we're running have been compiled by us, and we can make more guarantees at the compiler level. So we archive all this stuff so we can auto-tune it later, as I mentioned before. And so another new feature that we're coming out with is layers, and that means that we only actually have to build your application separate from the library. So we provision pre-built versions of all the Java libraries that you need, like the Java Developer Kit, the Graal Developer Kit for Micronaut, and all the dependencies is all pre-deployed and pre-built. So whenever you want to iterate on your app and roll out new versions of your app, you don't have to keep rebuilding the libraries underneath, and that's often 100 times bigger than your application code. And then, of course, whenever it's invoked, the application will download and start instantly. And if your application needs to pause, we'll swap it out of DRAM so you can reuse the DRAM and not charge you for it while you're waiting for some other service to do some work. And we'll auto-scale based on latency guarantees and not through some proxy value like CPU utilization or number of concurrent requests. And then all the cloud integration is just kind of handled for you. So we want to restore the Java programmer abstraction. So you just write some Java code, hello world. That's all you need to know. You don't need to know about all these other kind of cloud services underneath the covers. And so we also then want to avoid your need to learn about all these cloud abstractions like Kubernetes and how to deal with a lot of the expense of rethinking how you program because you're happening to target the cloud. And so there's a lot of operational kinds of things as well we don't want to have to do. I don't want you to have to pick Java heap size or code cache size or metaspace size. There are a lot of Java parameters that you need to specify if you want to get the best performance from Java. Like we don't have to do that. We don't want you to have to size a VM. Like typically today, if you want to run on a cloud serverless platform or any platform, you have to say, okay, I want a gigabyte of memory. This is the shape that I want it to run on. I don't want to have to reason about cold starts. And I also wanted to upgrade the library dependencies for you when we find security vulnerabilities. We want to be able to just auto upgrade them, auto patch. And over the longer term, we have ambitions to do a lot more interesting things like automatically refactoring larger services into microservices for efficient scale up and scale down. We also want to kind of automatically move database-centric logic into stored procedures. And we intend for future versions of GraalOS to actually run inside the Oracle database as well as outside the database. So the way it works, the load balancer picks a free host for a new request. We used to call this thing the orchestrator, but basically we find an available process on each host. We create what we call an isolate. And then we'll fetch this is hard to read here. We'll fetch like the shared object from network storage, and we assign what we call a memory protection key. And this is a new feature that Intel introduced like about 5 or 6 years ago, maybe a little longer. And what it does is a memory protection key allows you to subdivide the address space of a process, and such that if you try to access something outside that subdivision, then you'll get a segfault. And so you can partition the address space. You get a 4-bit key basically on every page in the OS. So what you do is you assign one key to each isolate, and so the isolate basically can't access data from outside of its subpart of the address space. And so it's a much lighter weight way to do isolation than to use processes and virtual machines. Which means you have to do IPC and a lot of other overhead to switch between processes and virtual machines when you want to move resources back and forth between them. We then kind of identify how much CPU and memory we want to assign to each isolate. In the common stateless scenario, we just blow those away as soon as the request is done, and you're getting a new copy of the isolate on each request. And then the other thing we want to do is we have this event management thing that I'll talk about in a second. Oh yeah, so yeah, the request comes in, you got the cool animation here. And then we find a spot where we can go run that isolate. Now I mentioned that we want to be able to run the applications in the Oracle database. And I think there's a lot of really cool opportunities there. I think Oracle's tried for the last 40 years, and I've been at Oracle for like 30-some years, to be able to get people to run more code in stored procedure in the database because it's so much more efficient. And people they know that stored procedure are more efficient, but they're like, yeah, they're such a pain to deal with, and I don't want to have to talk to a DBA. And there's a lot of kind of developer overhead reasons not to use stored procedures in databases. So they haven't ever been that popular unless you really care about performance in your database. So what we want to do is say basically, we're not going to tell you we ran it in the database. So you give us a microservice like that could run on a serverless platform in the cloud. Because it's stateless, it's actually very easy for us to transparently move it to run inside a host that's in the database kernel. And so the control plane could do something like run 1% of your traffic in the database and 99% out of the database, measure the cost of both versions, and if we see that the database is, in-database version is a lot more efficient, and enough efficiency is gained to basically overweight the fact that the database CPUs are more expensive. Like if it's a net win for you in terms of dollars, we could just transparently move it and then run 99% of your code inside the database and just keep 1% outside just for reliability and redundancy reasons. And so we did some recent tests, and this is just to do like a lookup by key and insert a row. And we have a version of Micronaut data that we basically ported onto to run directly on the data layer of the Oracle database. So you're bypassing the SQL engine and just going at the transaction management layer. And so that actually avoids a lot of overhead, as well as the overhead that you get from doing a network round trip and serializing into some format, and then walking all the objects with pointers, and then deserializing on the other side. And so it's like ridiculously much more efficient. It's like 300 times faster to do find by key, and whatever. Yeah, it's like similarly faster here. And then of course when you want to run On a local host, it's faster than if you're talking to another machine with a little more distance in the network, and so like those numbers add up very quickly. So if you can if you can run simpler kinds of database applications in the database transparently, we think this is going to be really a great way to get some efficiency. So we built this all on Micronaut data, which if you aren't familiar with Micronaut data, which it's basically the same as Spring data, what they do is they encode a simple SQL query as a Java method name. So you say find book by title, and that's the same thing as select from book table where title equals blah. And so that simple kind of encoding allows you to run, make the simple stuff simple. And we can actually convert those to a simple query plan, execute that query plan in Java code in the database, bypassing the SQL engine. No networking, no serialization, no SQL interpreter, and then you don't even know that we did it for you, which is, I think, the only way people will agree to run code in the database if we don't tell them. So that's kind of the idea there. So, I think there have been a lot of discussions about startup time, and why we care about startup time is really, I think, in particular in serverless, when you want to deal with a cold start, right? And so if you have nothing provisioned, I just got a blank computer, and I want to, with some just a version of the OS on it, some base image. The things that contribute to the cold start time, first you have to load the code over the network. Then you have to initialize the compute isolate. Like you have to boot a VM. Like you can run Firecracker to boot it faster. You can run Docker, exec. Some of those things take hundreds of milliseconds to run. Then you have to initialize the JVM, and you have to initialize the framework, Spring Boot and Micronaut or whatever, Quarkus. And then those have other libraries that may want to initialize themselves. All this Java code is starting to initialize itself. And then once you initialize all the Java code, then your application code sometimes needs initialization. Like it's going to have reference data, list of all the countries in the world, list of all the states in the United States, or mappings between zip codes and streets and those kinds of things are often cached in Java hash tables. We did analysis of where people waste memory in Java programs, and it turns out over 50% of what people store in JVM memory is just hash tables, usually filled with data from a database. It's just cached because they want very fast lookups to that data. So those all things are contributing to cold start because I can't actually serve a transaction until I've got my cache warmed up with all the hash tables that have metadata to tell me whether or not I can validate an address. Is it a valid country or not? So all those things need to be part of the cold start problem, or fixing the cold start problem. So Native Image helps you reduce startup time a lot for the Java parts of your stack. Native Image also helps you reduce the time to load code over the network because you don't have to, the images are smaller, there's no JIT compiler in there, there's not the second copy of the control logic. The way things work normally in Hotspot, there's one representation of your code in Java bytecode and a second in the compiled code after it's compiled to the machine code. So you kind of have two copies of all your logic once you've kind of compiled most of everything. And that's bigger, and it means you need more memory. And then if you want to cache that stuff, like if you're using AWS SnapStart or Creo or one of those kind of things, that's actually just moving work from the runtime startup to the download because you made the downloads bigger, right? And then this gets ridiculously small with native image layers, and I'll talk about that in a second, because of the way we build programs today. GraalOS has its own lightweight isolation mechanism that I mentioned based on memory protection keys, so that's really, really fast. And then the other thing that we have is what we call the auxiliary image heap. So you can basically create a second Java heap that basically just gets mapped into your process as soon as it wakes up. Preload it with data objects, and that's another way to avoid the cost to initialize your application. And then the other thing that kind of is a waste of time is when your useful program starts to call APIs and the API calls are slow, your program may be sitting there burning cores and DRAM seconds while you're waiting for the response. And so there's often another service called a workflow engine, like AWS step functions, that you use to break up your program into these separate steps. And so you just, you make your call and you exit, you write any state you have out to object storage, and then like every time you want to like make a blocking I/O, you have to kind of write your state out manually to storage, and then ask the cloud to wake you up again to run a second program when that first call comes back. And that's a horrible way to write code. So what we want to do is just suspend that for you automatically. Turn off like the meter on the cores and DRAM while you're waiting for the response, and then as soon as the response comes back from the slow service, we'll wake you up and then give you some cores again, and then you can go. Because we're really good at cold starts, it allows us also to do fast suspend and resume. So I got results actually this week from the GraalVM Native Image team, and just to show you the kind of things you're going to be able to see with layered native images. These are still early results, and this is just a hello world type of program. And you can see here, if you're familiar with GraalVM Native Image, that there's actually two compiles we're doing here, two native image builds. And the first one here, I say I want a layer. So I'm building a layer. In this case, I'm using a module, java.base. So I'm just building this native image layer. It's just like a shared object in native code world. And basically I end up with like 110 megs of machine code from compiling java.base, and I put it in what we call a layer. And the layer, we call it a layer because you don't have as many options to compose it. In the first version, we just kind of have like a base and an extension layer. And later we'll give you more flexibility, but we do need to kind of have them in a hierarchical fashion. You don't quite get as many mix and match opportunities as you do with native code, at least now. And so one of the things that we do when we do a native image build is we do a static analysis. We look at all the possible reachable methods and fields, and that's what we use to kind of optimize the program. So the results of the static analysis are actually saved in this layer.json file you can see here as a result of the first phase. And then when you build the application layer, you have to give us the results of the static analysis of the first phase, right? And so, so when I'm building the hello world, like the actual application code is, doesn't need to be very big. And so, yes, in Java native image world, we've reinvented shared objects. Yay for us. And so, but for a Java programmer, this is really interesting because so much of the code that we use when we build our applications is actually coming from libraries. And most of the apps that we've seen, you have like 100 lines of library code for every line of application code. So people running really simple CRUD programs, just insert, delete from the database, a couple thousand lines of application code, that'll end up being a couple million lines of code when we have to give it to GraalVM. So it's very nice if we can separate out the library code from the application code, and then I don't have to stream all the library code out every time when I want to like cold start your program. So anyway, that's your hello world program here. This is still early, so yes, it shouldn't be 2 megs to keep around the application, that's just doing a system print line. So we still have some bugs to fix here, but this kind of will give you an idea of the way it works. You can see that the time to generate the application code is also much faster because you're just compiling the application. I don't have to recompile and reanalyze the base library. And so that's a super huge thing for people that have been building with native image for a while. Yeah, you want to take a question?
So how do you optimize the base layer if you don't know how it is used in the application?
Yeah, so the base layer is a more generic compilation, right? And so it's not going to be as optimized as it would have been if you compiled the whole thing together, right? So we need to have more versions of the code. Effectively, there's a generic path as well as the specialized path, and we have to keep in all the generic paths. So that's one of the reasons the base layer is bigger, right? Because we have more compiled copies of the same logic effectively sometimes. And then when you compile the application code, we can decide to like ignore what the base layer compilation did and inline some of that code into the application if it's a useful thing to do. And so this actually may recompile really stupid things that the base layer code did. But most of the time, the generic code is actually pretty good, right? And so that's kind of I guess the heuristic that we've learned about is that, yeah, I mean, the base layer compile, the generic compile is good, and as long as you don't care about the a little extra space overhead for the base layer because you pre-provisioned that, then there's no real loss effectively. This is still early. We still have a lot of optimizations to do. There's a lot of hacks that were used to produce these results, but you can kind of see the direction that we're going in here, which I think is really interesting. So the other thing that happens when you you start up an app in the cloud, right, is you have to go often connect to a bunch of different services and get authentication tokens and like log in. You're just logging into lots of other different systems, and they want a lot of different credentials to log into different systems. You need a credential for object storage and a credential for, actually to get credentials from the secret defaults, you need a credential for that database. And these all take time. Like it often takes like 4 or 5 seconds just to warm up a typical cloud control plane in Oracle, just to make all these round trips to go like talk to other cloud services to kind of get some state. So basically we have this proxy server that works inside the GraalOS host that caches a lot of that state for you, so that I'll call it cloud application level stuff that is really common to all cloud applications. We're effectively caching it for you. So while in general, I told the team, don't use caching, as a way to like make your optimizations better, because that's usually a problem. In the case of the cloud state, network level things, we are doing connection caching, and that way you can keep the startup time low, because basically the GraalOS infrastructure has already pre-connected all that state that you need to run a cloud program for you. The other thing that's really important is waiting for completion events. There are a lot of asynchronous events, asynchronous processes that happen in the cloud, like, I would like to get another VM. Give me a 4-core, 8 GB VM. And you may wait minutes for that to come back and give you a VM. That's an extreme case. There's many other services. Give me a new object storage bucket that can be slow, that can take multiple seconds. And so a lot of those asynchronous APIs you need to either pull for completion, or you can try to get a signal from a cloud event, which is sometimes implemented and sometimes not. So what we actually do in GraalOS is we implement basically event management for you. So we'll either pull for some okay, great, that worked. He knew what was happening. Okay, yeah, and so like the proxy, one of the things that the rules, the security people make us do in the cloud is every connection between two hosts has to be over SSL. So any, even, it's not just SSL to get from like your computer like on the other side of the internet into our cloud. You have every connection between a pairwise set of VMs in our cloud has to be running over SSL. So we don't want to have actually just doing all the crypto stuff and certificate management, all that crap. We want to have that done for you, so you can just do the application code. Now, when I first got into this space, I was like, why do we have to have these stupid timeouts? Like, why is the cloud killing me? Like, if I have work to do, and like we actually talked to customers who tried to take conventional programs and run them on serverless, and they were like, oh, let's say that there was a network slowdown, and so like I was uploading a file, and the file upload took too long, and so like the cloud killed my program. Why is it killing me? Why is it killing my program? And the reason is kind of a bin packing problem for how they're managing resources for you. So it's easy to allocate resources when you're growing, because you can just greedily allocate cores and DRAM. But when it's shrinking, you get fragmentation, right? And so, well, how's the cloud going to efficiently use computers? What you want to do is basically migrate things and keep them packed down into using fewer computers, as the usage goes back down again. Now, you can do migrations. VMware has migration stuff. VM level migration is a thing, but it typically takes a while to do a migration because the size of the address space may be big, and that often means app downtime. Sometimes there are problems because the VM doesn't really know what's in the address space. It moves too much memory. The app may use some local machine state that breaks after moving, and this can, in practice, limit the utility of app migration. Serverless, answer is just to kill the programs and to force them to timeout so that you never have to repack, because these guys are just going to drain away after they hit their timeout, right? So So we wanted to kind of make app migration as a built-in feature so that we want to keep your application state most generally in network attached storage. And so we'll keep the Java heap mmap to a shared file. And then we want to migrate. We basically take a checkpoint. It kind of works like a database hot standby. Then we only have to pause to move the dirty pages. The garbage collector is smart enough to like stop moving things around that kind of trick the dirty page algorithm to moving more pages than it needs to. And then we can move the front end connection in the load balancer. And then sometimes we have to actually tell you that we broke a connection for you and reconnect, and sometimes the proxy server can handle it for you. Now, a really interesting part of cloud programming is these workflow engines. And so workflow, I think, is kind of like, it's an interesting intersection of Java, databases, and cloud technology, right? So the problem is that when you have service A that makes a call to service B, and service B has some state, like service B is going to write a record to disk and send a response. What happens when the return is lost? That response gets lost, and service A doesn't realize service B did the work. So you want to, if it just retries, you're going to get 2 copies of the record in the database or in storage, and that's bad. So you want to have this run exactly once semantics, and depending on what's crashing and when exactly it crashes, a bunch of different scenarios that workflow programs are trying to address. But this is basically the same problem as a normal database transaction, right? So the only difference is that rather than checkpointing data, like I'm moving $100 from my account to Sean's account, and I want to make sure that money's not created or destroyed if there's a crash, this is basically I'm storing Java programs execution state, like how far I got through the control path right before I did the API call or not. So effectively what I want to do in these workflow engines is checkpoint the Java program state to storage on every API call. So I think that's a really interesting thing about workflow engines. There's some startups in the space like Temporal.io and I think Azure has durable functions that aren't really very integrated with the JVM, and they don't know how to serialize the JVM very well. And so they kind of expose a lot of the guts here into the programming model, and we don't want to have to do that. So we want to just make it completely transparent as long as you're using the Graal stack, that these things happen. So if you just make an API call with Micronaut, we automatically, underneath the covers, we'll checkpoint it for you. Now the interesting extra requirement you have for these workflow programs is you want to be able to query the state of the program, because once I'm starting to keep program state in a persistent store, then that persistent store can have bad things happen to it, and I want to query it. Like find programs that are stuck waiting for an object storage bucket creation, or and it's a very similar kind of thing we have in database to find transactions waiting for a lock. So we want to be able to query on persistent program state. Find me all the programs that are stuck at this particular stack trace, right? And actually have that available to the SQL engine. We can query it. And so this kind of cloud program, actually the most optimal way to run it is in a database process, because you want very low latency calls to the I/O subsystem, which exactly what we always provision database servers to do. We want lots of IOPS, lots of IOs that you can do, because every time I'm making an API call to a distributed program, I got to go write some bytes to a disk, right? And database shapes in the cloud are usually very good at doing lots of I/O. So the serverless model doesn't have to be stateless, right? And real applications that we've seen, and I think it's been a problem for uptake of serverless, is the stateless requirement. And enterprise apps have lots of cache reference data for validation, which slows warm up. And you can use a service like Redis or Memcached to keep this around, but people still don't like that because, I still have to go over the network. I just want Java objects. And so, everyone just copies all that reference data into Java hash tables. And so, auxiliary heaps are a way that it's a native image feature. We can basically cache, you can have a separate file just with a chunk of your heap in it. That's created separately from the main application build of the code. So you can basically have an extra .so that would be full of data and not just code, right? So we want to use shared objects just with pre-provisioned hash tables full of code. That would be a shared object, and you could do that in maybe once a day you wake up and see, hey, have any new countries been added to the UN? If any new states been added, those things change very infrequently. Have you added new regions in Oracle Cloud? There's a lot of reference data that's very tolerant of staleness, and so those kind of things, are actually updated less frequently than you updating the code in your app. And so I think that's a really good way to, again, minimize the amount of startup time you need for more stateful apps. Okay, so comparison with like the functions as a service model, which I think most of the cloud vendors have now. It's a limited programming model, and it's not something that directly gives you access to the network. So I can't build a distributed program on like Lambda, because one function can't talk to another function. There's not a routable network endpoint there. So I think that's, and because they're stateless, you don't run long, and there's no state. I mean, they are all kind of restrictions. We want to make them all go away. And of course, it's more expensive. And so we're actually going to have a stateful version of GraalOS that's going to come out in a second state that we've been working on. And I think that's a way we want to take the serverless model, make it more generic. Java app servers are a very general model, but I think the problem that they've had was that they relied on Java isolation. And so you can't really trust an app server to keep multiple tenants isolated from one another because they're all in the same JVM. And that wasn't giving you isolation if you have native code. Even for Java code, the Java Security Manager was not secure against side channel attacks like Spectre and Meltdown. So for a lot of different reasons, like the Java app server model has been, mostly end-of-lifed. But I think the memory protection key feature actually allows us to kind of give you some of the best features of app servers to keep untrusted code in a different address space that's still in the same process. That's actually very useful for us running code in the application in other contexts, like running code in the Oracle database, or you can run Graal in NetSuite, where you provide some little bit of code that's running in the same address space as application code that has lots and lots of state in it. I still want to keep that trust boundary, but I want to still keep it in the same process so I can exchange data back and forth very quickly. Java app servers are really bad at scale to 0. App servers with no work to do still burn compute. We want to make sure that, like, if there's no work to do, there's 0 cost. Of course, GraalOS is integrated with the cloud, and so we can do a lot of other things like autonomous patching and autonomous tuning. One of the current restrictions of GraalOS and Native Image is that it's really designed for applications that are a little smaller with less than 32 gigs of Java heap. We are going to allow that to be, an exception for stuff you put into a cache layer, and that's a whole other story. But generally, what we want you to do is keep the size of your application small enough that we can move it around between servers quickly, just because of physics and network bandwidth. And we want you to then, as long as it's cacheable, I can move you from server to server. And if I blow away the cache, then your application is already designed to be tolerant of cache misses, for, like, say, business object caches. And so that's kind of the app telling us, I don't care about this data, and you can migrate without moving the cache with me. And then I think the comparison with containers and Kubernetes is that the infrastructure can do more. We can auto size your Java heap. We can do a lot more tuning. We can auto PGO your programs, and so like, the nice thing about the Java VM abstraction as opposed to the container abstraction is that we're allowed to recompile it. We're allowed to retune it. All those JVM parameters are just suggestions. And so we get to change those things for you, if that's kind of the abstraction we're promising. We also give you an ability to auto patch. And because we can integrate with the CI/CD pipeline, we'll rerun your tests. We'll redeploy in blue-green. And so we want to kind of automate all these things that make it costly to operate a cloud service. So like, we don't want you to have to keep VMs running when there's no work to do. So like, we're not going to keep a serverless runtime going after the request is done. We're just going to kill it instantly, and that will keep the price lower. And these kind of overheads multiply when you have services calling other services. What you'll see today is that, like, a dedicated VM and maybe putting Kubernetes on top of it is much cheaper than running like Lambda or functions. Just if you go look at the pricing on all the vendors, web pages, you'll see that. But if the workload is moving up and down, then you run into problems. And you have to over provision. And what you see in the cloud is lots and lots of over provisioning. So you start off with something like Lambda, and then you realize, oh, my workload's getting smoother and smoother. I'm actually successful. I'm getting more customers. And then I have to rewrite from a serverless platform to Kubernetes, and that's not trivial. there's a lot of infrastructure cost benefits. I don't have pricing to announce or anything yet, but we believe that that's going to be a lot better. So I think I talked about the first point already. We're going to basically try to avoid, as part of the curated stack, libraries that have to do initialization at runtime. And we want to help your application pre-prepare any initial state that it needs before it can service transactions, right? Like reference data. GraalOS has another limitation that currently, it's basically designed for either Java or native code, or another language that runs on the Graal platform. And we're only supporting native image. Not going to support running hotspot in GraalOS. You could run something else, like you could run a Golang program, but because we're not going to be able to directly integrate with the Golang garbage collectors, we're not going to auto-tune them. So you're going to see some degradation of performance if you use another language. And fundamentally, like the rules are of like where the network bandwidths are now, and you don't want to keep your memory footprint too big. Even if you're writing a stateful application, if you want to get good migration performance, right? And you can throw extra stuff in Micronaut cache for optional data that we can flush on suspend if hard pressed. Now I've used one word here in describing GraalOS, which is Java based, and that's kind of a vague term, so I want to help make this more defined. There's two senses in which GraalOS is Java-based. So even if I'm running a JavaScript program or a Python program or a native program on GraalOS, there's a bunch of infrastructure that's Java infrastructure, right? So we're expecting a garbage collector that we can use to move the knob between more RAM, less RAM, and higher latency, lower latency, right? I can give the garbage collector more buffer, and then it's going to get better latency, but I'm going to spend more on DRAM, right? That trade-off is something we're assuming is going to work. We're assuming that you're going to get telemetry with Java Flight Recorder and some of those other things. And we're basically defining the system call layer, like what system calls we're virtualizing by whatever Java needs, which is roughly the common denominator between Linux and Windows. So you don't get semaphores or shared memory segments or a bunch of kind of inter-process communication features in Linux that don't exist on Windows that aren't the same. That kind of simplified the virtualization project for us. So the common denominator of OS APIs used by Java is the OS API that we support. So you can run native code, but if the native code you need is not needed by Java, then we may not have virtualized it. And then the second thing is, so the two ways that it's Java-based is Java infrastructure, and Java defines the OS level API. Why have we done all this integration with the Java framework? Like, why do we care about frameworks? Why not just support Spring and Helidon and Quarkus at the same level? And the answer is, well, we want to be able to immediately translate between an HTTP call and a local function call, and maybe rebalance over the long term. I mentioned that workflows are nice to kind of instrument the way HTTP calls are done. And so the platform is getting very integrated in the way HTTP function calling conventions are done. And we're going to work with the other framework teams to be able to generalize these APIs, but it is kind of pulling the AWS, OCI, and Google Cloud today. We're working on Azure. That'll come out later this year. We will have a stateless function service based on GraalOS, hopefully later this year, targeting Java apps initially. We'll support other languages later. So the first version is just stateless, I said, so it won't have suspend and migrate. We aren't going to have the stateful stuff. Those are all being worked on, but not part of the first release. The transparent migration to the database being worked on. Demo available. I don't know when it's going to release. Some of the auto features are not there yet, and some of the optimizations that are reducing average cost as opposed to worst case cost are coming later. So the summary of the project is it's a full stack cloud platform. We want to rethink about Java as a platform and not just as a language, right? And that means you need all the other pieces to build your application. The three components are native image, GraalOS, and the Graal build, the Oracle build of Micronaut. Scale up, scale down, and optimize your database usage for you. And everything's all built, optimized, and supported by Oracle. So thanks very much. Volker has more questions.
Thanks for very, very great talks. Thanks a lot. So do you have more details, like technical details on GraalOS? From my understanding, like you have the hardware, then you have the virtualization like KVM or Xen, then you might have something like C groups or containers. Is my understanding correct that GraalOS is above this layer? It's like a
No, all that stuff is integrated in. So GraalOS implements C groups. We've implemented our own virtualization layer. So GraalOS, you can think of it as it's like a new version of the system C library that runs in conjunction with the JDK. So it's providing isolation for you.
But
so
does it need a kernel, or does it have its own
everything's in user space. So we're actually moving a lot of the stuff that Linux does into user space code.
Okay.
Okay, so like the fact that you're using memory protection keys to isolate these different programs, that means that scheduling between those two things is all being done by, we have this thing called the Graal visor. The Graal visor runs in process with the applications. Okay, and so it's just like, it's a privilege mode. If you remember like how VMS and mainframes have had kind of like these different privilege levels you can run in the same process, memory protection keys allows us to reinvent that.
It's basically like KVM virtualization, which runs as a user program in user space, but emulates a full.
It's not a Linux kernel though, right? So we don't want to support everything in POSIX. We just want to support what's necessary for Java.
Okay, so is there more technical information available on the details?
There's not a lot more technical information available because we're still trying to make it work. Once we make it work and release it as a product, then we're going to have like an open source version of in particular the isolation layer. I think is of general interest and something that people that want to like pound at our security isolation model are going to want to do. So we have a number of universities been working with on GraalOS that that's how we exchange IP with them. So we'll have an open source release at some point once we've kind of gone through all of the. I mean, the last 6 months we've just been trying to get the security model like locked down enough that we don't think it's going to be hacked.
Okay, thanks a lot.
Any other questions?
Yeah.
Thank you very much for the presentation. You mentioned auto-tune.
Yeah.
How is that related with PGO? Are you profiling what is running and making?
Yeah, so it's profiling while it's running. There's a lightweight version of the profiler that's a sampling-based profiler, so that's just going to be always on. So we're always getting a kind of a sampled profile, so it's not going to be completely accurate, but you make up for it with more data. And then we'll see, okay, your profile looks different than the profile that was used to build your program. And when we see that drift in the profile, then we could trigger an auto recompile.
Okay, thank you.
Any other questions? I guess it was just so comprehensive.
All right, good. Yeah, I had a lot of detail. Thank you.